Greetings, chemistry nerds. Let's get reviewing Unit 2. Part 1, we'll see. Maybe I can do a little bit more than I thought, but it's a cool little background. Alright, chemical bonding. Let's go. At this point, you should know that the three types of bonds are ionic, covalent, metallic. Keep in mind that an ionic bond is between a metal and a nonmetal. Right, the metal will be the cation, the nonmetal will be the anion. Covalent compounds are between two nonmetals. The ionic compound is from the transfer of electrons, cation to anion. So we'll have one electron being transferred to the element from 1 to 1. When you do so, remember it becomes stable because the outer layer disappears, and underneath you have a full octet. And the anion, when it gains the electron or electrons, fills its octet and becomes stable. So they end up with 8 valence electrons. And there's this electrostatic attraction, right? Coulomb's law can be used for that, where you have the positive ion attracted to the negative ion. Right? Opposites attract. Again, ionic compounds, the transfer of electrons, metals versus nonmetals, cations and anions. And that is the ionic bond. Covalent bonds are the sharing of electrons between two nonmetals, and this is due to the getting 8 as well. So they want 8, and they share it kind of in between them to get 8, and that fills their octets up. And then you have the metallic bond, which is the sea of electrons with the kind of the nuclear positive cores. They get the delocalized electrons. They become kind of more of a cation, so it's the attraction between all these metal ions and nuclei and the sea of electrons. And it's the sea of electrons, this flowing of electrons that allows metals to be good conductors of electricity. Let's see, did I forget anything? Hopefully not. I'm doing this swimmingly, I suppose. In valence electrons, you should be able to look at a group number and give me the valence electron number. That should be something in second nature. But I suspect if the College Board asks you a question on this, they're going to... I don't even know how they'd ask it. Alright, as far as... You might see these diagrams on there. These are potential energy versus distance diagrams. So these are often used to give you a way to figure out the bond length and the bond energy to break it. And if you don't know what's going on, they look kind of confused, like what the heck? But these diagrams, you're going to look at the bottom, the trough here. So as we go higher, right, this is a kind of a repulsive force, and down below the line is an attractive force. And what this is really demonstrating is as the atoms get closer together, right, this is distance, right, bond length. As they get closer together, those nuclei get closer together, and those positive forces start repelling each other. So that's what this upper part is. And as you pull them apart, you get this attractive force. You get to maximize the attractive force. If you pull apart too much, right, again, looking at Coulomb's law, they don't feel those attractive forces as much because the distance is greater. Remember, it's r squared, so distance has more of an impact there. So you're really, just looking at this diagram, you're going to put the distance at the bottom, and then that will be the length, will be on the x-axis, will be the bond length. Oops, hit the button. And the energy will be on the y-axis, will be the energy of the bond energy. So right here, bond length, bond energy. This is a classic hydrogen kind of graph. We have they're too close. The atoms are too close together here. They're repelling. Here and then here we have the maximum attractive force, and then here they're too far apart. So these diagrams, more likely to see that than asking you to identify something as covalent or ionic. Although they might do that with intermolecular forces, but let's move on. All right, bond strength and bond length. covalent bonds, the strength is going to be in the bond. The more bonds you have, the stronger it is. Single is triple bond stronger than double bond, stronger than single bond. And then bond length is also associated with that. One term to be aware of is bond order, which is very similar to using bond the types of bonds: single, double, triple. So bond order 1, single bond; bond order 3, triple bond. This is kind of a shortcut for that. You might see that. But anyway, triple bonds are shorter than double bonds, are shorter than single bonds. And the more bonds you have, the tighter the fit. They're pulling together more in the bring in, and the length shrinks. The one catch here is with the with resonance, where you have you may look on the Lewis structure like you have a single bond, but that bond is rotating, and since that double bond is not fixed on any one structure, you're going to have a hybrid between the single and double. So that bond with the resonance would be shorter than a single, but larger than a double. Ionic compounds and their strength is going to be tied to the ionic charge. The larger the charge, the stronger the attraction. In Coulomb's law, smaller the charge, smaller the attractive force, and that leads to properties like melting point. The larger the charge, the higher the attraction, the more energy it's going to take to break it and make it a liquid, which is going to increase your melting point. And then smaller ions will also be kind of stronger because you have that distance between the ions is lessened, so they're going to be a little bit more compact than the larger ions. So you may see a comparison here. Why is this compound have a higher melting point or boiling point than this compound? And it's going to go back to, if it's ionic, it's going to go back to the charges and the size of the ions. It's covalent. It will most likely be kind of the intermolecular forces, whether it's polar or nonpolar, that kind of thing. Or a hydrogen bond. Can't forget the hydrogen bond. And here we have the ionic solid. Two more things to talk about. Just the general ionic solid. That's the crystalline shape. They're arranged in a particular way, and the way that they're arranged is different for different ionic compounds. There's different shapes and there's different amounts. It's not always a 1-to-1 ratio. Like sodium chloride here actually has a 7 valence, 7, but here it's you can see for every 1 chlorine ion there are 4 sodium ions, and the same with sodium. There's 4. I think the actual number of it is, I don't forget. It's not important. And it's a regular repeating pattern. And the net charge on an ionic compound is always 0. But if you dissolve them in water, you break up the ions, so then the charges exist. So as a solid, the net charge is going to be 0. This is a good little diagram of electron transfer. You get the ionic charges. You lose the shell, still have a full octet, gain 1, and you get the larger, you get the 8 octet. The last structure we need to talk about, and then I'll let you go, is our metallic alloys. You have the substitutional alloy and the interstitial alloy. Substitutional alloys replace similar sized atoms with the actual metal, whereas interstitial alloys have the atoms smaller and they fit in between the spaces. So here I have gold, 14 karat gold. You have a silver atom, which is the substitutional atom, taking the space. And then for steel, you have carbon, it's smaller than the iron, and it's kind of fitting in between those spaces. So substitutional, similar size, interstitial, smaller, and fits in between those spaces. All right, have a good one.